we are, or how close we are to achieving this, let's say, real turbulent kind of behavior. So that's the goal here. Okay, let me start from a question. If you look at these two flames, right? So this is a premix flame at a certain jet Reynolds number. This is a non-premix flame, again, a certain Reynolds number. You think these flames are turbulent, okay? And I mean, after looking at this result for quite a while, I convinced myself that these are really not turbulent, right? That if we really learn something about the physics of the flame at this Reynolds number, we might make some mistake, okay? So that's a little bit the point here, okay? So I show you three examples here. The first one is a non-premix set of flame, where we look at the differential diffusion effect, a bunch of premix flame at increased Reynolds number, and where we look at the turbulent flame speed, and some application of training machine learning model with different flames. And yeah, so let me start from this first test case. So this is a series of DNS that I did a few years ago. They are large, but not unbelievably large, about 500 million grid points. They are very complicated because they have a lot of species, a lot of stuff included in terms of the physics. And what I'm going to do, I'm going to compare two cases. One is, let's say, a DNS with all the physics, so with a full diffusion model with mixed average, and a case where the differential diffusion is ignored, so using unity Lewis number. Okay. So if you look at this flame as they evolve, this is one of the two flames. So these are different instant in time, which given the type of this configuration, this means that the Reynolds number is increasing in this direction, right? So you can think about this time as different flames at different Reynolds number that increase in time. And if you look at the statistics of the two cases, red is mixed average, blue is Lewis 1, you can see that a low Reynolds number for early time, these are different while they go on top of each other, okay? Now you see that you need fairly high or enough high Reynolds number to get to the point, right? I mean, you might think that this difference between the two cases are fairly negligible, but if you try to learn something about this, for example, in terms of modeling, you realize that you have to be careful. So the dots here, the two colored dots, are the two DNS, the two turbulent flame. As I said, when the Reynolds number is high enough, they coincide, right? Now, let's say that you want to understand which flamelet model you want to use to represent this flame in the best possible way. Well, you end up concluding, if you do things properly, that the Lewis 1 flame is what you should use, right? So if you do things properly, if the Reynolds number is high enough, the information that you extract here, well, you should use a Lewis 1 flamelet, which is something that we usually do, that we usually know, but this is a direct proof, okay? If I was using the low Reynolds number case, I would have concluded the opposite, that I should have included differential diffusion in the flame, which would have been the red line, which is a mistake, okay? So that's an example here, right? That using low Reynolds number condition might be inappropriate sometimes, okay? Another case here, this is a series of premix flame, and where the Reynolds number is doubled every time for each flame. So something like 3000, 6, 12, 20, 22, okay? So this is the flame that I showed you before, okay? When I ask, is this turbulent? Well, when you look at this compared to that, now, well, you start to think, maybe that's not really turbulent, okay? And again, these are fairly large simulations. The last one on the right has about 23 billion grid points. If you count all the variables, it's about 500 billion degree of freedom. Very large, run on a lot of computer nodes and so on. Okay, so we did a lot of things with this DNS. One thing we looked at is the turbulent flame speed. Okay, which is defined here in the standard way. Computed in different location of the flame and so on. And also we can compute what we call the stretch factor. So this is the degree of proportionality between the flame speed and the flame area. Okay, it's a way to isolate the different effects of wrinkling of the flame and the different local burning velocity, like what Christian was discussing also in the hydrogen, in the talk about hydrogen. Okay, now we did the analysis. You can see a few things here, right? So this is the turbulent flame speed as a function of the streamwise direction in the flame. So as you go in this direction and from one flame to the other, so different lines here are the different flames at different Reynolds number, as you increase the Reynolds number, okay, the flame speed increase. Okay, that's kind of expected because the area increase, as you can see here. So this is what you would expect. However, if you look at this I naught there, which is this stretch factor, the proportionality of the lack of proportionality between these two, if you want, okay, you see that this thing increase with I naught, sorry, with Reynolds number. Now, these flames have been designed such that they have the same Karlovitz number, okay? If you take, I don't know, any book in combustion, most likely you will see a sentence like that this thing shouldn't depend on the Reynolds number if the Karlovitz number is fixed, okay? So again, this is a kind of a surprise result, and it would have been very difficult to see this kind of behavior if you were limiting yourself only to the low Reynolds number cases and so on. So again, trying to push the Reynolds number has been a key here to understand what was going on. You can go even in more detail, and you can plot all these results in a more synthetic way to look at scaling. Okay. Now again, this is the scaling of these three quantities: the flame speed, the area of the flame, and this stretch factor, plotted versus the integral scale. Now, given the way this simulation are designed, the integral scale here is basically the Reynolds number, okay? Because U prime is pretty much constant, okay? So what you see here, and probably the most interesting thing here is the scaling of these colored dots. So the colored dots are the flame speed and the area. And what you see again here, if you go in this region, which is basically low Reynolds number behavior, you see that there is a very strong increase, which is actually exponential, okay? If you go to Reynolds number which are high enough, okay, you push it as much as you can. So these orange dots here are for the highest Reynolds number flame, okay? You end up in a different regime, okay, with a sort of almost linear proportionality between these two things. And if you go on Peter's book, that's what you should expect, okay? Again, if you go to low Reynolds number DNS, you might fool yourself thinking that you discover something new, while the actual physics is different, and it's actually consistent with what it should be at high Reynolds number. So again, this is another example of pushing the boundary of the Reynolds number. Last example I want to show is a little exercise we did with machine learning. So we considered, again, using the same set of DNS, a typical LES type of equation for combustion. It's a progress variable transport equation where you have to close this term, right? The reaction rate. And of course, there are classical ways to do this. Another option is to use a neural network where you train with DNS data with the filtered C, and then you train the neural network to compute the filtered reaction rate. Okay, this is something that's been done by various groups and so on. And what you do? It's a usual thing, right? You take the DNS data, you compute the reaction rate, you filter your stuff, so you have a set of training data for the filtered C and for your quantity of interest that you need to close, and you train a neural network with an input and output, right? We did this with a CNN using a certain architecture and so on. The details are not very important. Actually, this is the CNN we use. It's a fairly simple CNN developed by Corentin Lapierre in Surfax. And of course, we did our homework. We tested it, we tried it, and so on. And we found that it works very well. Okay, so this is model prediction, DNS target value. Okay, it works. And then we went a little bit more in detail. We took these 4 flames I've shown you before, these 4 DNS or premixed flame, and we did all the possible combination, right? So we took low Reynolds number flame, low Reynolds number flame training, and then we tested the model on the low Reynolds number flame, okay? And then the second Reynolds number trained, applied the model to the second Reynolds number, the model trained with the first one, okay? So all the 16 possible combination of training and testing with different data, right? It's a first attempt to generalize to high Reynolds number, okay? So ideally, if you want to use a machine learning model trained with DNS in real application, you have to make sure that your data are sufficiently turbulent to be representative of your final application, right? So we were doing this exercise here for the range of Reynolds number we had, okay? And here's a summary of what you get, okay? This is the error that you get from the machine learning model as a function of the Reynolds number. Okay, 4 lines here are 4 CNN model trained on flame 1, flame 2, flame 3, flame 4, applied to flame 1, flame 2, and flame 3. Of course, when you train a model on flame 1 and you apply it to flame 1, works very well. Same for the second, same for the third, and so on. Okay, the interesting thing here is to extrapolate. So let's take model trained on 1 and apply to all of them. And as you go towards higher Reynolds number, the error increases, right? Of course, you are extrapolating. You expect that the error increases a little bit, but the problem is that this thing is really going up a lot, okay? So if your gas turbine is probably in the Reynolds number of, on this graph will be on the second room there, well, your error will be unbelievably large, okay? Now, if you look at the next one, okay, you see that the extrapolation error tends to decrease, okay? The best way to look at this is probably to go from this point to this point for the blue line. So a jump of 2 in Reynolds number, okay? A factor of 2 from 1 to 2 has a certain error. If you go to the last one, the red one, again, a jump of 2, okay, has much smaller error, okay? So that means that the extrapolation performance gets reasonably bounded if your starting point, again, is a high Reynolds or a Reynolds number which is high enough, okay? So again, pointing out the fact that we realized already looking at the data that the low Reynolds number flame might not be turbulent enough to be representative of turbulent, okay? And these are just conclusions, nothing else than what I said before. I'll leave it there so we have a couple of minutes for questions. Thank you very much.